I'm going to find the analytic solution of the ODE y prime is equals to x squared subject to the condition y at 2 is equals to 4.2. And then I'll go on and compute and plot the numerical solution using ODE 23 along with the points of the analytic solution in the interval x from 2 to 4. So for me to do this, I'll click on my live editor here, then click on code. Now enter the code for solving this ODE. So for me to do that, I'll start by creating symbolic variables. So it's syms, and you are creating a variable y, which is a function of x, and the variable x. And then click on the return key. And then the next step is to enter the equation. So it's eqn, and that is what I'm calling the equation. So for the equation, it has the derivative there of y. So it's a diff, open parenthesis, y, and then comma, then indicate we are differentiating with respect to x. So that's our derivative there, and it's equal to, so it's double equal sign, and we have our x to the power 2. So I'll put in my x to the power 2 there. So that's our differential equation. I can just run so that we can see, and we have our equation here. The derivative of y with respect to x is equals to x squared. And then now we are given this condition here, y when x equals to 2 is 4.2. So I will need to enter that condition there. So for me to enter that condition, I'll call it cond is equals to y at the point 2 double equal sign is equals to 4.2. So that's our condition there. I can just run. So we have our condition there is y at 2 is equals to 21 over 5. It wrote it there as a fraction. And then I'll go on and use the command dsolve to obtain the solution. So I'll click on the return key. And for my solution, I'll call it ay. Because I'm saying the analytic solution of y. That's why I chose this notation here. So ay is equals to d solve, open parenthesis. We are solving what? We are solving the differential equation that we've just entered. And under which conditions? Under this condition that we just entered here, which we called cond here. So I'll go on and run. And we would have our solution there is x cubed over 3 plus 23 divided by 15. So that's our solution here. I now go back now to my question, which is saying compute and plot the numerical solution. Now we have obtained our analytic solution is this one. Then we go on and compute the numerical solution. So for us to do that, I'll click on the return key, then create a function. So for creating a function, I'll call it ODE function fn is equals to, and then we put at the @ sign, then open parenthesis, and we are having our independent variable is x, our dependent variable y, and then specify the differential equation. What is on the right hand side is x squared. So we'll write x to the power 2. Then I'll go on and run, and we have our function here. And then click on the return key. Now for us to obtain the numerical solution, we need to enter the interval for the x. X is varying from 2 to 4. So I'll call it x span is equals to, and then put my 2, then colon, and then specify a step size. I'm going to use a step size of 0.1, then colon, then indicate where we are ending. So it's 1 to 4. And then I'll just put on a semicolon just because I don't want the result to be appearing on the screen there, because we'll be having many values. So I can just click on run here, then click on the return key. And the next step is to enter our condition. Our condition there is y at the point x equals to 2 is 4.2. So I'll go on and write that as y naught. So I'll call it y 0 is equals to 4.2. So that's our y at the initial value there with just a semicolon there. And then now go on and obtain the numerical solution. So for the numerical solution, I'll open brackets, Yeah. And I'll specify the output that I need. So I will need my xn, then put a comma, would need yn. Yn here I'm specifying the numerical solutions of y. So is equals to, and then we type in ODE. We are using ODE 2, 3, then open brackets, and we are putting the ODE function that we have just written here, then put a comma, and then put the span for the interval. We called it x span, so it's x span, and then comma, then we put in our condition, which we have called y is 0, and then I go on and run. So the solution, what will give us is, it gives us values for x and the numerical values for the y, the solution there. But there are many of them, that's why you are having dot, dot, dot there. So what I can do, I can just put a semicolon here so that I suppress that result there. Because what we need to do is we need to go on and plot the numerical solution together with the analytic solution. So I'm now going to the stage of plotting the solutions. So for us to plot the analytic solution, we need the values of y, because we said for our solution here is ay is equals to x cubed over 3 plus 23 over 15. So we need the values of y for all the values of x from 2 to 4. So I'll call those values the analytic values. So I'll put an A, so values of y. So the analytic values of y, I'm just writing it in short here, is equals to, and we'll use the subs command, open parenthesis. We are substituting into what? We are substituting into the analytic solution that we obtained, which you called ay, then comma. Then we are replacing what? We are replacing x, comma, then put now the new values. The new values, we need the new values of x that we called x span, the one from 2 to 4. So it will be x span. So this one will give us the analytic values for the y. Then I will just put a semicolon, because the values will be many. I don't want them to appear on the screen. Then I just run there. But since I've put a semicolon, nothing comes out, but it has been computed. Then I now go on and plot now. So I'll start by plotting the analytic solution. So it's plot, open parenthesis. Then we specify what will be on the horizontal axis. What will be on the horizontal axis is what we called x span here. Then comma. What will be on the vertical axis is the analytic solution, the values of the y, and we called them a analytic values of y. These ones, those are the values. Then I can just go on and run. So when I plot, that's the plot that we have there. But I can just change the output of this one. I put a comma and then open the quotes here, and then put a plus, then change the color, say red. Because I want the analytic solution to be different from the numerical solution, then I go on and run. So we have the analytic solution is now being shown as a plus plus there. And then I'll go on now and plot now the numerical solution. For the numerical solution, we had called the values xn for the horizontal, then yn for the solution. So I'll go on and click the return key, then click on hold 1. Just because I want to plot that numerical solution on the same graph as this one. And our numerical solution, we plot it by using plot, open parenthesis, and we are saying our numerical values are xn, then plotting them against yn. Then I can go on and run. And we have now the numerical solution has been plotted as a single line here. The plus signs are referring to the analytic solution. Then the next step, what I can go on and do, I can label my axis there. So I will say the x label, then open parenthesis, what am I putting on the x, open quote, so it's x. And then I need a label again for the y, so I call it y label, open parenthesis, and then we are putting the quote, then y. Then I can just click on run, and you see that our graph now has the X and Y labels. We can even go on and put a title. So for the title, I'll call it a numerical solution of ODE. So I'll call it title, and then open parentheses, and then in quotes, we put the name, so it's numeric solution of ODE. So you just type in an appropriate title there. So it says numeric solution of ODE there. But one thing that we have there is we are having a red line and the plus signs. It might be convenient to put a legend there to specify what each of the things are denoting. So I can go on and type in legend, open parentheses. So for the legend, I'll open quotes, and inside the first argument, it puts the graph that was plotted first. The graph that was plotted first was the analytic solution. So what I'll type in there is the analytic. Then put a comma. And then the second argument is the second graph, the second plot, which is the numeric solution. So I'll type in numeric. Then go on and run. So our plot now has a legend there indicating that the plus signs are the analytic solutions and the straight line is the numeric solution. So what we are seeing there is no difference between the numeric and the analytic solution for this particular problem. So what we are seeing here is in this case the numerical solution is quite accurate.